Every answer from an artificial intelligence system feels weightless. A question appears on a screen. A sentence returns. No smoke, no engine, no visible machine. But behind that instant response is a physical system, chips switching billions of times, servers pulling electricity, cooling systems moving heat, and data centers negotiating with the grid. To understand the future of AI, we have to follow the power cable. AI needs energy because intelligence, at machine scale, is computation. During training, a model searches through enormous patterns in language, images, code, and data. During use, it performs inference, calculating the next useful token, pixel, recommendation, or decision. Each step is arithmetic. Each arithmetic operation is electrical switching inside specialized chips. One operation is tiny. Trillions of operations become infrastructure. The factory of AI is the data center. Rows of servers do the visible computing, but the building around them is just as important. Power equipment brings electricity in. Backup systems protect uptime. Cooling loops remove heat before chips throttle or fail. Networks move data fast enough for many machines to behave like one system. The scale is no longer abstract. It is industrial planning. The energy story has two parts. Training is the dramatic burst. Thousands of chips running together as a model learns from massive data sets. Inference is the daily bill. Every search summary, chatbot answer, image request, coding assistant, translation, and recommendation adds another small demand. As AI enters phones, schools, offices, hospitals, and government services, ordinary moments can become continuous load. There is a hopeful side. Chips get more efficient. Cooling improves. Models can be compressed, routed, cached, and matched to the difficulty of the task. But efficiency is not a magic erase button. When a service becomes cheaper and easier to use, people use more of it. Better machines can reduce energy per answer while total demand still rises. The hardest constraint may not be the chip, it may be the grid. A data center can be planned faster than transmission lines can be approved, financed, and built. Local communities may see jobs and tax revenue, but also competition for electricity and land. Every megawatt connects private computation to public infrastructure, so AI energy is not only technical, it is political. Electricity is only one part of the physical footprint. Computation becomes heat, and heat has to go somewhere. Some data centers use air, some use liquid cooling, some depend on water systems that matter deeply in dry regions or during hot seasons. The environmental question is therefore local as well as global, not just how much power, but where the heat and water burden lands. Clean electricity can change the meaning of AI energy. A model powered by low-carbon energy has a different climate footprint from one that depends on fossil backup at the wrong hour. But buying clean power on paper is not the same as building reliable clean supply on the grid. The question is whether AI demand accelerates cleaner infrastructure or simply competes for electricity that others also need. If energy is part of AI, then accountability has to measure it. Useful disclosure would show how much electricity is used, when it is used, where it is used, how much carbon is associated with it, and what water or grid constraints are affected. Without measurement, every promise sounds clean. With measurement, schools, hospitals, companies, and governments can ask whether a system is worth its physical cost. The point is not that AI should stop using energy. Hospitals, climate science, accessibility tools, safer infrastructure, and better education may all justify serious computation. The point is that energy makes the trade-off visible. If AI is going to consume more electricity, then we should demand more value, more transparency, more efficiency, and cleaner power in return. AI should be useful enough to deserve the energy behind it.